Hello, mentors. Welcome to part 2 of meeting 5 simulations, and in particular, item 2 explorations. The main two goals are find a balanced state in which there is little segregation, so a lot of integration, and this will work like a puzzle. And then harder, undoing segregation. How do I do that? Undo by creating new systemic rules into this game. So the first one is more like a puzzle, closed-ended, using the rules. And the second one is actually bend the rules or propose new rules to achieve something that's right now impossible. Let's take a look at how students will read them in the student workbook. The first one is called stable paradise possible. Can we place the shapes in a way that they're pretty mixed and all are happy? For example, with a 70% tolerance. So if it's too hard for them, then they can try maybe 80% tolerance. But if they want to be really challenged, they can go for maybe 52 or 60% tolerance. So there's a little bit of freedom there, but the default would be 70% tolerance. Here they will write their findings, how they did it, what principles or strategies they used. And then game changer, how could we introduce reasonable rules that allow us to move from a board that has lots of separation to a board where shapes are more mixed? Let's take a look at the idea behind each. So as we said, the first is a puzzle challenge with many different solutions. We don't have a formal definition of mixed, so a particular rule, but of course it's something that students could see and intuitively, tell. Since students should understand what separation is by now, they do plenty of exercises by now. Now they want to try to make sense of integration, the opposite of separation. And you can have like a contest and gamify it and say whoever makes it more mixed wins. And you could have a judge, right? Or a voting system so that clearly maybe one or two of the works of the students in these groups are the winners. Now, if you want to be kind of mean and put it really to the test, once a group has some stable, happy configuration, let's say of a tolerance of 70%, you could say, okay, now shapes just became more intolerant, and now the tolerance is 10% less, so 60%. What happens? Maybe they're still happy, but maybe some will be, oh, now I want to move. The second, the game changer, it's the following important. Make sure first that students really understand this irreversibility property. Once you got to something stable, everyone happy, and probably with lots of separation, even if you raise the tolerance level, even if you raise it to 100%, you won't go back to mixed state. So if I'm happy right now with a tolerance of 70, then of course I'll be happy if the tolerance is 80%. Because if I'm happy with the neighbors that are not like me, then if I'm more tolerant, of course, I won't be unhappy. So you cannot reverse. And that's a problem. If you lower the intolerance, then you get even worse, right? You get even more separation probably. So you need an incentive rules, new incentives or new rules if we want to go to integration. The key connection is part 1, 3 new worlds. Do it only if they need it. So this is called just-in-time help, not just in case. So in just if it's needed, do it. Don't do it by default. In other words, you want to bring productive struggle so that they're a little stuck maybe, and they're like, what do we do? And then after some struggle, you could say, remember this part in which we had this part of the rule, I am also unhappy if all my neighbors are like me. I kind of get bored. I need diversity. And then they could come up with a rule that's numerical in terms of a percentage. So let's take a look now at some of the solutions that we could see. Let's go to this part. So first, for paradise possible, he would be such an example in which for 70%, every shape is happy. For example, this here has 3 and 3. It's fine. It's happy. Let's take a look at some that looks kind of not too good. Maybe this one here. It has 1 out of 3 of him. So 2 out of 3 neighbors. So it's this case. It only moves if all are unlike him, because that would be, with 2 is just 66.6%, and it's high tolerant, so feels happy. So you can check if we didn't make any mistakes that everybody here, it's a happy shape. Something important is that even if one shape is unhappy and move, it may trigger other shapes to move and unstabilize the whole map. So that's something also that you could discuss with your students, the fragility of this when we don't have the other rules as we were discussing. Okay, so for game changer, they could come up with this diversity rule. I am unhappy if more than 80% of my neighbors are like me. In particular, if all my neighbors are equal to me, right, are the same shape, I will need to move to get at least one of the non-like me shapes. And then you could summarize, or students could summarize that this is a range from 30 to 85% of equal neighbors, right? So that's the percentage of equal neighbors. And I need at least 30%, which is the complement of 70%. But I don't want to bump it into 100%. I want to keep it lower than 85%. This is reasonable, right? It looks like a reasonable rule that the shapes could actually adopt. So I hope you have fun in these explorations. Quickly, next meeting, so meeting 6 on November 13. We'll return to these ideas in maybe other maps, other types of territories, namely square 2-dimensional maps. So there's another chance for you to keep exploring this deep math. Okay, thank you, and see you in another video. Goodbye.